All right, everyone, let's get started with class today. People on Zoom, can you hear me? That's a fun noise. All right, so last Friday you guys took an exam. That's exciting. Relatively, how are we feeling after that? Okay, we have minor response. Most people are staring blankly. Okay. I did send out a exam reflection form last Friday. I think that about 5 of you guys have filled that out. So if you could fill it out by the end of class today, that's very helpful. I think it's helpful for you all because it gives you a chance to reflect. It's helpful for me because then I get a more individualized idea of all of your guys' exam experiences. So please do that. It'll be a great time. Other than that, today we're going to primarily focus on those alcohol lectures at the beginning of class. I know that you guys potentially may have watched some of the ether videos yet. I have a feeling that a lot of you guys haven't because I know a lot of you pushed off this new material until after the exam, which is totally okay. I also would have pushed off the new material until after the exam. But that's why we're going to primarily focus on alcohols, make sure we have a good grasp on those today. All right, does anybody have any logistical questions before we get started? How was everybody's weekend? Did you guys get to take a break? It's really that point in the semester where everything just is constantly going. This weekend, I worked on my senior thesis a lot, which is really great that I made progress on it. But also I feel like I'm just so tired. I'm just like, guys, let's just take a break for a second. But instead we're gonna talk about alcohols, which will be so much fun. So just to get, yeah, sorry. The last I heard is that the grades should be up sometime today. So I believe that's still the case. I haven't heard any changes on that. But to make sure that we're all on the right headspace, that we have the proper mentality when going into exam 3, there's something I'm going to talk about. So with exam 2, there were 5 total reactions that you guys could have been tested on. You learned about E1, E2, SN1, SN2, and radical halogenation. Now, exam 2 was very much of an introduction into reaction mechanisms, introduction into synthesis. With exam 3, you're going to learn a lot more reactions. So I think that today at the beginning of class, we're going to go over 6 reactions. So this is 6 reactions just from one set of lectures. So there are going to be significantly more reactions on this exam. And with that, we need to really make sure that we're focusing on what's important. So what is important to focus on is we need to think about, for each reaction, the starting material. So what starting material is required for a particular reaction? Furthermore, what functional groups need to be present in the starting material? Does the substitution of the alpha carbon matter? We need to think about the products produced. So is there a retention of stereochemistry? Is there an inversion of stereochemistry? What functional groups are present in the products? Things along those lines are important to consider there. And then we need to think about the reagents that we need to go from the starting material to the products. The last thing to think about is the reaction mechanism. Now, I know reaction mechanisms can be tricky, and a lot of you are still adverse to them. You don't really like them that much, and that's okay. My goal, though, this semester is to get you to be familiar enough with reaction mechanisms, comfortable enough with them, where you do like to use them and where they're able to help you out. So these are the 4 things that we want to think about. That's only 4 things. That was 5 fingers. This is 4 fingers. So there's 4 things that we want to think about for this exam. So without further ado, we can get into talking about our alcohol reactions. So there's lots of things that we're going to be able to do with alcohols, and this slide divides them into 3 chunks. We can generate alkoxides, we can make alcohols, and we can activate alcohols. And over the next slides, we're going to really get into more detail about what is happening with all of these different techniques. Also, just as a note, we're actually going to do this right now. So I'm going to stop sharing my screen real quick. We're going to go on to Moodle because I feel I still have some students that are confused about how to access the lecture notes and the worksheets over Moodle. So we are going to clarify that right now. Okay. So this is our course Moodle. We can go back to the very beginning, just so you guys get the full experience here, the full experience of how to get to Moodle. We go to Chem 199. Then you want to go to Chem 232, because that is the class you are enrolled in. Then you want to click on my name. I am Kaylee. And then we're on this slide right here. Now this is a little bit tricky, I'm not going to lie. Like, it confused me at first. But if you want to see the exam 3 information, you got to click on this little arrow. And it is all there for you. So there's the lecture notes and the worksheets. So that is how you access them. I know some of you guys know how to do this, and this is just review, but just to make sure everybody is on the same page and everybody has access to the same resources. Okay, that being said, we'll go back to talking about our reactions with alcohols. So our first reaction that we can do with alcohols, the first thing that we can do is we can generate alkoxides. What is an alkoxide? So this boy right here, this is an alkoxide. An alkoxide is a very fancy name for any sort of O- species. So for exam 2, we typically refer to them as RO-. We learned that these are good nucleophiles. They are also good bases. So one way is that we can convert an alcohol into an alkoxide, and this is a simple acid-base reaction where we have our base come in and just steal that hydrogen. We push those electrons up onto the oxygen. Now it's very important to make sure that the base you use is able to deprotonate the alcohol. We want to have a base that is strong enough where it is able to deprotonate that alcohol, because alcohols are really poor acids. They have a pKa of about 16. So you want to use a base that has a pKa that is greater than 16. So examples of these bases are negatively charged nitrogen, LDA, T-butoxide. We saw these both in exam 2. And then sodium hydride. So sodium hydride is a hydride base or a hydride reagent, which means that it's going to exist as Na+. And then a hydride is a hydrogen with a lone pair. So this is a hydride. So generating alkoxides, that would be step 1 of this reaction mechanism. Step 2, this is the Williamson ether synthesis. Williamson ether synthesis. If you guys have gotten to the ether lectures, you know what I'm talking about. If not, we don't need to worry about it yet. But this is an SN2 reaction. So what this is telling you is that after we generate an alkoxide, That alkoxide can then react via an SN2 reaction or an E2 reaction, or other reactions that we haven't yet learned about. So how do we feel about that? Alkoxides are great. We love them. Moderately. Okay. So next we're going to talk about synthesizing alcohols. So there's a lot of different ways to synthesize alcohols. We talked about how to synthesize alcohols with exam 2. We talked about how we could have a primary alcohol. Wow, no, because why would we synthesize an alcohol if we're starting with a primary alcohol? That makes 0 sense. We could have a primary alkyl halide that we react with hydroxide, and we can produce an alcohol that way. We also talked about how we could have, so this would be by SN2. We also talked about how we could have a tertiary alkyl halide that we react with water, and that's another way that we can generate an alcohol, this way by SN1. Not if you are following this. Nobody nodded. Okay, you guys have very tiny nods. Okay, does anybody have any questions on this idea of generating alcohols with SN2 and SN1? No, okay. So, but the problem here lies in the fact that if we think about that giant table at the end of our E2 lecture notes, we know that hydroxide is also a good base. So we can do SN2 with hydroxide at a methyl carbon or a primary unhindered carbon. But the second we get to primary hindered, we're going to get E2. So that's not very helpful. We want to be able to generate a diverse array of alcohols. So what happens is this mechanism that we're going to talk about, the synthesizing an alcohol with a masked hydroxide, is beneficial because it allows us to synthesize alcohols on these primary hindered and secondary carbons. Granted, we can also use it for primary and methyl alpha carbons, but in particular, it's the only way that we can synthesize alcohols for primary hindered and secondary carbons. So the benefit, or the reason why we care about this technique so much is because we're using sodium acetate as our nucleophile. Now, sodium acetate, good nucleophile or bad nucleophile? Good nucleophile? Good base or bad base? Bad base, yes. So we know that this is a good nucleophile and a bad base, which is great because that means that we can't have E2. We can't have E2 because we need to have a good base to have E2. So this first step of our masked hydroxide mechanism is just a simple SN2, where we're going to kick off that good leaving group. And we're going to generate this guy right here. Which I mean is all great and nice and dandy and stuff, but like that's not an alcohol. So that's a problem because the whole thing is that we want to generate an alcohol. Well, this is where we have this second reaction, this SNAC, come into place. So this first step, this first reaction is SN2. And then we're going to start our SNAC reaction. So let's go ahead and change its color. Let's do orange. So I'm just going to copy down that material. Exactly, and we're going to go over the SNAC mechanism. So with SNAC, what we're going to do is we're going to react with hydroxide. So if we overall wanted to draw kind of a generalized reaction, we can say that the first step is SN2 with sodium acetate, and the second is SNAC with sodium hydroxide. We can have that hydroxide come in and attack. Now, for the purpose of exam 2, we talked about nucleophiles attacking the alpha carbon, the carbon alpha to the leaving group, which, yeah, that's an electrophilic carbon. But a carbon that is even more electrophilic is the carbonyl carbon. So you'll see this a lot where we have nucleophiles coming in and attacking that carbonyl carbon, which is what we're going to have take place here. If we form a bond between the alcohol and the carbonyl carbon, we need to break a bond. And that's going to generate this tetrahedral intermediate here. Once we generate this tetrahedral intermediate, we're going to want to reform that oxygen-carbon pi bond. An oxygen-carbon pi bond, or a carbonyl, is stable. We want to get the most stable compound. So we're going to want to reform that bond, but in order to reform that bond, we need to kick something off. We need something to act as a leaving group. So carbon doesn't have 5 bonds. Now, if we think about what we just did, in the previous step, we just made that carbonyl OH bond, that green bond. So we don't want to break that bond because we just did that. Why would we take our hard work and put it to naught? So what we're going to do instead is we're going to break this bond right here and push those electrons onto the oxygen. This is going to generate an alkoxide, our O- species, as well as acetic acid. Let's erase that because you can't see that very well. We'll draw it over here, as well as this acetic acid. Then in our final step, in order to generate that alcohol, we're going to have that alkoxide deprotonate our carboxylic acid. And we'll produce acetate and our alcohol. So how do we feel about that? Does that make sense? Do we like this? Thumbs up? Okay, so people that don't have thumbs up, does anybody have any questions right now? Okay. So I'm going to go ahead and flip to the next slide then. This is just a prettier drawn out version of what I just drew because it looks nicer. So that's there for your future reference if you want it. So just to kind of summarize things that we can do with alcohols, this in particular looks at the substitution of the alcohols. So if we have a methyl or primary alcohol, we can do SN2, but we can also use this masked hydroxide mechanism. If we have a secondary alcohol, we cannot use SN2 because E2 will dominate. And if E2 dominates, we're not going to form an alcohol, we're going to form an alkene. But we can use that masked hydroxide mechanism. If we have a tertiary alcohol, we can't use SN2 because you can't do SN2 at a tertiary alpha carbon. And we can't use this masked hydroxide mechanism because that masked hydroxide mechanism requires that SN2 happens. So if you have a tertiary alcohol, you need to rely on SN1, in particular SN1 with water. All right. So the next couple slides, I promise there's not that many slides left. I know I've been talking for a while. But the next couple slides are going to talk about activating your alcohol into a good leaving group. Now, the best thing about this slide right here is this is something that we've already talked about. we've already talked about how we can use a acid to protonate an alcohol and turn it into water. And we've talked about how water is a phenomenal leaving group. So this is just a reminder that we are still going to have to use these ideas that we learned with exam 2 again with exam 3. So one thing that I want to touch on real quick is this idea of a non-nucleophilic acid. So a non-nucleophilic acid is an acid like H2SO4. If we want to dehydrate an alcohol, or if we want to form an alkene, why is it important that we use a non-nucleophilic acid? So an example of a nucleophilic acid is something like HCl. And the reason why it's important for us to use a non-nucleophilic acid is because if we were to have this reaction right here, we were to activate this alcohol with HCl, if we have a nucleophilic acid, we're not going to get elimination because we have a good nucleophile. So because we have that good nucleophile, we will see substitution instead. So this is just kind of a subtle note with why we need to use H2SO4 as our acid for elimination, because we want to make sure that it is a non-nucleophilic acid. Yeah? Yeah, so the question was, is H2SO4 the most common non-nucleophilic acid you will see? And yes, I think that you only see H2SO4 as a non-nucleophilic acid for organic chemistry. I don't know why, but that's the only one that you have to care about. HCl, HBr, HI, these are nucleophilic acids because we know that our halogen is a good nucleophile. So does anybody have any questions up until this point? Are we still hanging in there? Okay, so this is just another summary slide that talks about the substitution of your alcohol and what reaction will take place. And just as a note, when we do have secondary and tertiary alcohols, we can have elimination happen at these carbons, but we will have it happen by E1. So make sure that you watch out for that. Okay. So then we're going to talk about 3 additional reactions. So these last 3 reactions are reactions to convert our alcohol into a better leaving group. Now, like what we did for exam 2, where we really emphasized the importance of telling the differences or finding the differences between SN1, SN2, E1, and E2, we're going to want to do it with these 3 reactions as well, because there are certain times, certain reaction conditions where you would prefer one of these mechanisms over the other. So the first way we can talk about activating alcohols is using PBr3 or PCl3. Now, phosphorus, this phosphorus right here, that is a very electrophilic atom. So what happens is your alcohol can actually act as a nucleophile and attack that electrophilic phosphorus. Now, after we have that attack, we generate this good leaving group here. And then we have an SN2 reaction where our leaving group can come in and kick off, where our bromine can come in and kick off the leaving group. So with this reaction right here, it is SN2, which tells us two very important things. Important thing number one is that it's going to tell us that it can't happen at a tertiary carbon. So we cannot activate a tertiary alcohol using this mechanism. And important thing number two is if there's SN2, there has to be inversion, which means that if we had a reaction that looks like this, we could not use PCl3 for this reaction because we have a retention of stereochemistry here. So so this cannot happen. This is bad. So we have to make sure we have an inversion of stereochemistry to activate alcohols via this technique. The next technique that we can talk about is very similar. This is using thional chloride. So this is thional chloride. So thional chloride is SOCl2. This reaction is very similar to the one we just talked about, where again, it's SN2, so it can't happen at a tertiary carbon. And we also have an inversion of stereochemistry. Now, there's not really a good way to prioritize using PCl3 versus SOCl2 because they result in the same exact product. So with those two, it's kind of like both of them are equally okay. Both of them are equally adequate to produce that chlorine as long as it is not a tertiary alpha carbon and as long as there is inversion. Does anybody have any questions up till this point? No, we're still alive. Okay. So then there's only one more reaction that I want to talk about, and that is with our sulfonate esters. So we can also activate alcohols with our sulfonate esters, and this is not SN2. This is SNAP. So that means that with activating alcohols with our sulfonate esters, we have a retention of stereochemistry. So if we want a retention of stereochemistry, we have to use this technique. Now, if we look at this slide over here, this is a screenshot from Axelson's slideshow. I think that the slide for the semester looks a little bit different than this slide right here. But the molecules on the left, these are the reactants. These are the things that you're going to add to solution with our alcohol. So we can see in this case, I added mesyl chloride. Whereas the things on the left, or excuse me, the things on the right, these are the actual leaving groups. So we would say that this leaving group right here is a mesylate leaving group. Now, for the purpose of exam 3, Axelson does want you to be familiar with the name, the abbreviation, and the structure for all 6 of these molecules. Thankfully, they're at least a little bit similar, where these guys are kind of the same, these guys are kind of the same, and these guys are kind of the same. So it's a little bit less to memorize. Now, does anybody have any questions? Yes.
Like under the mesyl chloride, the ring with the nitrogen, what is that called and why do you need it?
Perfect. Good question. So the question was, let's erase all of these random scribbles. What is going on with this right here? So this is a weak base. And it's called pyridine. So we need it to basically, over the course of the reaction, it needs to be protonated. So it kind of absorbs acid, it absorbs protons in solution. So it is just used as a weak base over the course of the reaction. So you actually not only need pyridine for this reaction with your sulfonate esters, but if we flip back to the previous slide, we also need pyridine for our reaction with thionyl chloride. So does that clarify your confusion? Okay. Does anybody else have any other questions? No. Okay, perfect. So then I'm going to go ahead and stop sharing my screen and